So if I were to,
So at the beginning of every problem, it said something, especially in chapter 3, about Newton's what was it called? Newton's template, and it said, yeah, the first step is to draw a sketch showing the situation. Draw out each word problem.
okay, so that's what motion diagrams are falling under. So if I were to show you a motion diagram that looked like that, how do you interpret that?
Speeding up acceleration, more distance in between the dots means that it's getting faster.
Right, but in this case it's going this way?
Or slower
Right.
in this situation, yeah.
Perfect. So these are your velocity vectors. So this would be v1, v2, v3, etc. These are your points. And each point is taken at the same amount of time, right? So then if you were to draw acceleration vectors, what would they look like?
Just the opposite. They would start out with less space in between them.
Well, they'd be going to this way, right?
What do you mean?
Acceleration vectors. So the acceleration of this, you said it was this way?
Well, I don't understand.
Okay. So like we said, these are the points. This is where the position of the particle is. And this is the velocities. So the acceleration is the change in velocity each time, right?
Yeah.
So like if you look here,
Yeah.
see how that acceleration points this way? And then it shows this picture of, here's your original velocity, and here was the acceleration. So here's your new velocity. That make sense?
Yeah.
So because we're getting shorter, our acceleration vectors would look like that.
Okay.
And then just do that, okay? So let's look at one more example of this, because it seems like...
So they just... Okay.
So they show you which direction the velocity is changing, right?
Yeah.
So what about this one? What's happening in this motion?
So you're speeding up, so your arrow would be facing right?
Right? So your accelerations?
Yeah.
So that would be like your motion diagram. Cool, okay. So that's the basis of that section. Motion diagrams, you want to understand what it's doing. So then you could take this example, what if you were to do something like this? What happened here?
So it was going fast, it slowed down, and it sped up again.
Perfect. Okay. So let's move on from that. Seems like you got a good understanding of that. Okay, yeah. Then what else? Problem solving. This is that method you were talking about.
Yeah.
So you just make a picture basically. Okay, so let's skip past that one. We're doing good there. The particle model. Do you know what the particle model is?
I don't remember that.
So just read that sentence there, what it says.
Yeah, makes sense.
So basically, when it's talking about the particle model, this is the model that we use in all of physics. Or not all of physics, but this whole class. So that's where you take a car, like it's a big object, right? You actually have, acceleration and velocity all over this place, right?
Yeah, and so you're just gonna draw it at its center of mass. Is that the same thing as center of gravity?
Yeah, pretty much. With kinematics and stuff, it doesn't necessarily have to be the center of mass, but it's a good way to. But it's basically just taking this whole car and realizing that it's all going to move together and representing it in your problem as just a point. Does that make sense?
Yeah.
So if you have a car that's going down the road, instead of drawing a car at every point and trying to figure out what the car was doing, you just say, okay, here's my car. It goes this direction. So that's what the particle model is. Okay.
Why are your dots some open and closed?
Oh, that's just because I'm not coloring them in all the way.
Okay.
So that's just when I make a dot. Sometimes I don't fill it in all the way. Okay. So that's the particle model. And then motion along the line. Okay, so applications here. Let's look at this. So this is that pictorial representation. You draw a motion diagram, establish coordinates, sketch the situation, and define symbols. We'll go over that more in the next chapter. But if let's say your velocity is pointing this way. This is velocity. And your acceleration points this way. This is acceleration. What does that mean?
That you're slowing down.
Okay. What if your velocity was pointing this way and your acceleration was pointing this way?
You're speeding up, I think, in a different direction, I guess.
Yeah. So you're speeding up, but you're speeding up negatively, right? Because this would be a negative velocity. This is a positive velocity. So the key here is, so this is a negative velocity and a negative acceleration, right? This is a positive velocity and a negative acceleration. Then what else could we have? We could have a negative velocity and a positive acceleration. What's happening here?
So a negative velocity.
Just means that you're going to the left.
Okay.
That's all it means.
Okay. So you're going to be slowing down, right?
Okay. And then there's one other situation where you could have velocity is positive and acceleration is also positive. And that one's obvious that you're just going to be speeding up going this way. So this one, you said we were speeding up just to the left. This one we're slowing down. This one we're slowing down. And this one we're speeding up. So what do you notice about the signs of velocity and acceleration?
If they're going in the same direction, you'll be speeding up, and if they're going in opposite directions, you're slowing down.
Perfect. Okay. So I think that's pretty much chapter 1. There's a couple other little concepts, but they carry through enough that we can review them in chapter 2. So all this stuff so far, you've got. Okay? What about significant figures? Do you remember how to do significant figures?
Yeah, for the most part, I could probably use some review though.
Okay. So there's a couple rules having to do with significant figures. One is finding how many significant figures, and the other one is finding out how many you keep when you're doing like multiplication and stuff. So the first part, so if you had a number like this, how many significant figures do you have?
2.
Yeah. So you only count these 2. These zeros don't count. What if you change that number to this?
Still 2.
Well, you have a decimal point here.
Still 2, right?
Not, in this case, you have 1, 2, plus all 5 of these zeros. So here are your rules for finding out how many you have in a number to begin with. the first one is all non-zero digits are significant. So anything that's a 4 or 5 is significant. Okay? And then, what about, so let's talk about this one. 7, 0, 7, 3, 5, 0, 2. How many significant figures do you have in that number?
They're all.
Yeah, all of them, including these zeros. So we'll say zeros between significant digits are significant. Okay? So because this 0 falls between a 7 and a 7, it'll be significant too. And then the third one is what happens when you do this. You say 0.0630. How many significant figures do you think are here?
3.
Yeah, because you have this one. Which one of the zeros
The
is
one on the left, closer to the decimal.
this one?
Yeah.
Not quite. It's actually this one. Because trailing zeros after a decimal place, so after the decimal, are significant. Because what this means, so what's the difference between that number and this number?
Yeah. So the closer one to the decimal is still after the decimal, but just because it's not trailing, it's not
Right.
significant.
Uh-huh.
Okay.
So, because so if you write them in scientific notation, it gives you a better idea. Because, like, what about this number? How many significant digits does that have?
3, I guess, or 4.
Yeah, so it has these 4. None of these zeros count, because you could also write this as, you could write 5.720 times 10 to the negative 8. You see how that obviously only has 4?
Yeah.
So those are just kind of what you want to remember. The difference between this number and this number is this one, someone went to the trouble of finding out exactly how many, what is this, the 10,000th place?
Yeah.
So instead of saying,
Well, that would be 100,000, right? No, maybe not. Just kidding.
so let's see, maybe your ruler looks like this. You got 1, 2, 3, 4, 5. So this one could be like, not that it's to scale on this, but going only to that decimal place, that'd be kind of like if you're measuring a length that got to here, right? Something that was that long. You kind of, let's say this was 2 centimeters here, and our ruler continues on. So this would be 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8. This, what would you have to say that this length was?
Well, with no uncertainty,
Yeah, for sure how long this one is.
2.8.
Yeah, so you could only have, for this measurement, you'd only be able to put 2.8. You could only have those 2 significant figures. Now what if you had a more accurate ruler, and it had all these little lines in between, and what you're measuring came to right there?
It's still 2.8. Right?
But you know for sure that it's not 2.81, right? Or 2.79. So now you could say 2.80. So that's why the trailing zeros are significant.
Okay.
Okay, so, and then real quick, the rules for addition and subtraction. So if you have 32.75 and 6.32, how many significant figures can you keep in your answer if you add these?
2 or 1.
So you add them. This one has 4. This one has 3. But with addition and
Behind
subtraction,
the decimal, you can only keep 1, right?
no, actually, it turns out you can keep both of them.
Okay.
So in addition and subtraction, you just look to the right of the decimal place. Does that make sense?
No.
Okay. So if you're adding or subtracting something, you only need to look at how many decimal places you can keep instead of significant figures. So you could have this number and then add 4.563. How many significant figures can you keep?
After the decimal or
Right.
Oh,
After the decimal, sorry.
3.
Yeah. So you would add this and you'd keep your 1, 0, 1, 4, 7, 7, and then you'd only be able to keep 3 of these. So you'd have to drop that one basically. So you just round. But that's because all of these, what would happen?
So you would just make that last 5 a 6 then, and drop to 7, and then add.
Well, you would want to add first, and then, so what would this be, like 10147, so it'd actually be 8.1887, and then you'd get rid of that, and you'd round this up to a 9, right? Okay. The reason we don't only keep 4 is because then we'd only be keeping these 4, right? And then our addition didn't do anything because all of a sudden we'd have a 101.4. You see how much different these numbers are?
Yeah.
Yeah. But you don't need to worry too much about significant figure rules. It makes sense as you go. You always keep a legitimate amount of significant figures. And then when you multiply things or divide them, how many significant figures do you get to keep?
I would think the same. I think you get to keep 2 after the decimal.
So with multiplication and division, it changes, and you count all your significant figures. So in this case, you get to keep 3. So with multiplication and subtraction, you look at how many you have after the decimal. With addition and subtraction, sorry. With addition and subtraction, you look at how many you have after the decimal. With multiplication and division, you look at all of them.
Good.
So those are the significant figure rules. Okay, let's move on.